Here I want to talk about taking our integration by substitution a step further and look at how we'd apply it to definite integrals. Now, everything we've done up to this point hasn't been a definite integral because it's lacking in one set thing, and that's limits of integration. In order for it to be a definite integral, we have to have these limits in order to be able to calculate a precise value at the end of our work. Now, what we have to remember is something we covered back in higher, and that's the fact that we know that the integral is the way of representing the area either between two curves, a curve in a line, or a curve in the x-axis. So in a similar situation as to what we've got here. Now, A and B here represent the start and the end point of the area that we are going to look at. They're what's called the limits between which we integrate and which the area exists, i.e. this is the definition of a definite integral. And in order to calculate this area, we'd follow this formula here, where the area would be the integral from A to B of f of x dx. Now when we do this, remember we integrate f of x, we then calculate the value at B, the value at A, and we subtract the value of A from the value of B. Now, up to this point, when we've done it, we've always had limits. But now we have to consider these limits and take them beyond where we are. Up to now, we've always worked in terms of x, or a single variable at least. We haven't used any form of substitution. So our limits have always been given in terms of that substitution. However, once we substitute, we have changed the variable which we are working with. So we can no longer use those limits as part of our integration because they refer to a different variable than the one we're using. So we have to take this into consideration when we're doing our calculation. Let's look at this example here. So let's imagine I want to find the integral from 1 to 3 of 3x bracket 2x squared minus 1 all squared dx. Now, as I've said before, once we've done our substitution, which in this case will be for this, so let's state that it's u equals 2x squared minus 1, we'd still follow the same generic steps we've done up to this point. So take the derivative, so I'd get du is equal to 4x dx, and I then want to eliminate the x dx from my final bit that I'm going to work with. The 3 here can go in the front as a multiple of the integral. So what I'd then be able to say is I've got 1/4 du equals x dx. So I'd be able to substitute these in, and what I'd be able to do is change my integral to 3 times the integral of u squared times du over 4. Now that I've got that there, I have to look at my limits. Now the answer to how I deal with this at this point is quite simply get new limits. Now that sounds fairly generic because I can't just pluck limits out of thin air. I've got to somehow get them relating to this. In order to do that, take the limits in reference to x, substitute them into your u, so that would be my substitution here for u, and I'll get new limits out which refer to the values in reference to u. So I'll change the limits to reflect this new variable, and I can then use it from that point. So if I was to do that, I'd have u equals 2x squared minus 1. So if I substituted in x equals 1 for the lower limit, I get 2 times 1 squared minus 1. So 2 times 1 squared is 2 minus 1 would be 1. And for the new upper limit, I'd take the 3 here, and I'd do 2 times 3 squared minus 1. 3 squared is 9. 2 9s are 18. Take away 1, gives me a new upper limit of 17. What I can now do is integrate it and calculate my definite integral, but use these new limits of 1 and 17 to get my final solution. So integrating it, what I'd end up getting is 3/4, I've just taken the 4 out there, it's a common factor, times u cubed over 3. And that's between my new limits of 1 and 17. What I then do is I take this, evaluate it at these limits, and I should get a solution. So I'd end up getting 3 over 4 times, at the upper limit, so 17 cubed over 3, take away the value at the lower limit, 1 cubed over 3, and I'd get it there. Doing this would give me a final solution of 1,228 units. So there you go, I've evaluated the area under that curve between those two limits by doing a substitution and changing the values of my limits to reflect that substitution. Once we've done that, it's just following it through step by step beyond there in order to be able to calculate the final answer we want. And this is true regardless of the substitution we use. Let's imagine I want to evaluate the integral from 3 to 5 of 4x times the square root of x squared minus 9 dx. Now this is one of our standard substitutions that we use from before. For this one, what I'd substitute is u equals x squared minus 9. Take the derivative of this, and I get du equals 2x dx. But the part I want to get rid of is 4x dx, so if I multiply both sides by 2, I get 2 du equals 4x dx. What I can now do is stick this back into here, and what I'll change my integral to is the integral of, well, it's 2 du, so I'm going to put the 2 outside, since it's just a constant, of 2 times u to the power of a half du. What I now have to do is evaluate and calculate my new limits. So I've got to use the old limits of 3 and 5, substitute them into here to get my new limits, and then use those in my calculation. So my lower limit, let's call it u1, that's going to occur when x is equal to 3. And when x is equal to 3, what I'll get is 3 squared minus 9. So for that, I can say my lower limit is now going to be u1 is equal to 0. If I then look at the upper limit, so that again, let's call that one u2, I know that that's going to occur when x is equal to 5. So in order to get that, I can say that u2 is equal to 5 squared minus 9. 5 squared is 25. 25 minus 9 is equal to 60. So there you go. I've now got a new upper limit and a new lower limit, which I can use in my calculation. So now we just integrate it and then follow our standard rules. So up the power by 1, so I get u to the power of 3 over 2, and I divide by the new power. Well, dividing by 3 over 2 is the equivalent of multiplying by 2/3. So I'd have 2/3 u to the 3 over 2 between my two limits of 0 and 16. Now, u to the power of 3 over 2, remember, when we're writing that, that's the equivalent of doing the square root of u cubed. So bear that in mind when we're doing our calculation. What I can then say is fine, so that's 2 times 2/3 times the square roots of, at the upper limit, 16 cubed, take away the lower limit, which is 2/3 times the square root of 0 cubed. Now this is quite nice because this second part disappears. Square root of 0 is 0, this part will go away. Square root of 16 is 4, 4 cubed, then ends up giving me 64. So I get 2 times 2/3 times 64, giving me a final solution of 256 over 3 units squared. So there you go, area under the curve for that one. There's nothing against it being a fraction, never said it couldn't be that at all. Further example, let's look at a trigonometric one. Evaluate the integral from 0 to pi over 2 of cos squared x sine cubed x dx. Now remember, for this one, what we said was we take the odd power and associate one part of it with the dx, which will help us with our substitution. So I'd write it as the integral from 0 to pi over 2 of cos squared x sine squared x times sine x dx. So there's the part there associated with the dx. For this one, I'm going to take u being the other part. So in this case, what I'm going to let is u be equal to cos x. Then I can say du is equal to negative sine x dx. So negative du is equal to sine x dx. So I've now got a part there I can substitute in to get rid of this. I've got a part here to get rid of my u. The only thing I've got to get rid of now is the sine squared. Now remember, sine squared x is equal to 1 minus cos squared x. So that means that I can rewrite the sine squared x as being 1 minus u squared. So my integral then becomes the integral of cos squared, well that's just u, times what I've put for the sine squared, so 1 minus u squared. And then that's all going to be times negative du. Now again, I've got my limits 0 to pi over 2 in terms of x. I've got to use that to get my new limits for u. So u1, the lower limit, is when x is equal to 0. So if I substitute it in here, I get u1 equals cos of 0, which is 1. Second one I've then got to do is u2, and that occurs when x is equal to pi over 2. So I get cos of pi over 2, so u2, my upper limit, is equal to 0. So stick that now, part of my integration. I then have the integral, this time, from 1 to 0 of all of this here. Now, my limit goes from 1 to 0, so higher to lower. We can reverse that and make it go from 0 to 1 if we negate the whole thing. So that means turn it into a negative. However, I've got negative du here, so what that will mean is I'm just going to turn this to a positive du, and I'll get the integral from 0 to 1 of that, but without the negative here. Multiply out the bracket as well, u minus u cubed du. So now I just simply integrate this, substitute in the limits, and see what I get. So that ends up giving me u squared over 2, take away u cubed over 3, between 0 and 1. So if I substitute the limits in here, I get 1 squared over 2, take away 1 cubed over 3, take away 0 squared over 2, take away 0 cubed over 3. Now I know it's intuitive that because you're going to have zeros on top, naturally this would be nothing. Don't be tempted to ignore it though. Still write it, just to show that you understand that, but you can just then eliminate it at that point and say, right, okay, that's equal to 0, so I don't need to worry about that. So I've got 1 squared over 2, take away 1 cubed over 3. So what I'll end up with is a half, take away a third, so I'll get 1/6 units squared. So there we go. We've calculated that integral using the same standard substitution we talked about previously. Again, we've then changed the limits, integrated it, and then used those new limits in my calculation in order to get rid of what we need to get and calculate the new area as our numerical value. We have to remember that that's the key step, is this one here. If I have a new variable, I have to make sure my limits are written in terms of that variable. Originally, they'll be written in terms of x. We have to change that using the relationship between the two variables, which we develop when we pick our substitution for the calculation.